get to the full proof of Borel sphere, I think we will at least start it. This is a non-trivial theorem, also a Lang theorem. But I'll remind you to get a very long break. So I'll remind you some of it. So G, fine. Inclusion of G groups. So I'll remind that we may speak about the G invariance in A. It's a subgroup, and it's actually naturally a subgroup of the invariance in G. And also we have G action on the coset space, and we have some G invariant coset. Whenever we do have a coset which is G invariant, it gives us some twisted action on that copy of A. That is an element of G comma A. I'll omit the G times whenever G will be clear. And there is a natural map. B spaces. And this is exact. Actually, I can, in some situation, continue this not so long exact sequence. And obviously, when A and B are, I mean, these are H0, of course, and when A and B are abelian groups, or just G modules, if you wish, I can just go on forever and get this famous long exact sequence. And I'll ask this as an exercise, probably you didn't have the time to possibly solve it, but I'll leave this as an exercise. An important one, though, I want you to do it. And, maybe exactness, when I say exact, is in the non-abelian way. So all those guys are pointed sets. The special points here are the identity, the concept of A, and the natural A action on itself, natural B action on itself, etc. And a kernel of a map is a pre-image of the special point. And exactness means that the image here is the kernel, is the pre-image of this standard action of A itself, standard action of G on homogeneous space A, whatever. And the exercise was the following. Already before the exercise, let me explain something. So whenever I have an element here, a concept of A, which is G invariant, it will appear here as an action of A, a G action on A compatible with the A action, and of course will go to 0 here. And if I'll take another coset, but if you have, I don't know, BA is one coset, and then I will apply an element, I'll take some B prime, an element, and I will apply it. I will get another coset, but which will be isomorphic. So it will have the same image here. It will be as isomorphic as a GA space, because everything can be with G and A. So what I want to say is actually, I can model out the BG action here. This is the exercise. I want to say that the map from this to the kernel is actually BG invariant. So it's easy, I think, if you understand definitions, once you understand definitions, but also I want to say, and it is injective, and this follows from the long exact sequence without farther, but it is also onto. So the claim is that if every guy in the kernel you can achieve this way. So you should understand the concept of twisting that we discussed in order to do this. It is not hard at all, but I actually want you to do it yourself. And okay, so that is one thing we discussed, and then we had this.
No, but I don't understand. It follows from the exact sequence, from the exactness.
This is isomorphism. No, the exactness is only on the pointed sets.
So how
So the thing is that it's
maybe I'm missing
in the leading case, it's just the
in the Abelian case, yeah.
So maybe, okay.
Yeah, I mean, possibly I'm missing something stupid. I mean, in any case, I leave this as an exercise. This is easy. When I thought about it all the time, this thing. Oh, okay. Let me not discuss this anymore. And let me do discuss the following. So the setting of interest for us is. Finite field extension and we take V and F variety, so a variety defined over F, and maybe parenthesis, maybe we take some extra structure. For example, sometimes our variety are endowed with a group structure, with my disguise, algebraic groups. Or maybe the variety G is acted upon by some algebra. Maybe it is maybe it has an additive group structure, and it is acted upon by a field. Maybe it is a vector space, for example. Maybe it's five-dimensional algebra. Etc. And what we study is this theorem of Weil, saying that in that case, given that data, we can define the descent set of V with respect to this extension. So all those F varieties up to F isomorphism, which become the same as V after extending the scalars to E. So this is let me write this way. Let me think of if I do the exostructure given on V as part of the given exostructure. So this set answers the questions: what are the other variety with similar exostructure defined over F, such that after extending scalars they become the same as V? And of course, V is an element here, so this is a pointed set. And we've seen this natural isomorphism with I guess here there should be similar box. Okay, and now, of course, this is, for us, this is the thing that we want to understand, and we want to use general machinery of non-abelian cohomology in order to understand those sets It so happens that many times it is natural to study non-organic topology by itself, to develop some theory, and then to understand this. But also many times, for simple pieces, I do understand this easily and get information on that. So there is some zigzag that will happen in this class today. So let me start with some computations, for example. Are there any questions about? So far, it was a reminder. So assume in this example that the characteristic of the field is 0. And assume V is the additive group of finite dimensional vector space. So as a variety, it's the finite space. But also enjoy it with this extra structure. Oh, sorry. Actually, I will not be in that picture at all now. I will just look at this with V as a group. Okay, I'm not confused for a minute. Now I claim. Okay, this is an additive group. It is acted upon. Now G will be from now on. It's going to be and and now I want to claim that page 1, actually it will be page I. It's something I will need for I bigger than 0, page G, VE is 0. So we did it in a special case of a group acting on Rn. We've seen that if we have a finite group acting on Rn, whatever way, then H1 is trivial. Actually, what we did there is true whenever the characteristic is 0. And let me remind something about it. So V tensor E. So it's the E point. But now I think about it as a group. If you reach an answer, reminder.
So V is just a vector space over E?
Yes, this is just a vector space over O and with a natural G action. Well, it's a vector over F if you wish, and taking the E points. It's not exactly what. So the claim was that we did this not in that generality. So let me even go to a further generality. Let's A be a G module. At least a billion now, and assume G finite group size n my claim is that the map, I will use this several times. The map A goes to NA is trivial. In cohomology. H I phi is 0 as a map from H I G A. Zero. And the proof is more or less the same. Of course, I have to ask Roman again for explanation. So let me remind it. This one. I should memorize this. Just to give you a conceptual explanation, we can do it as the following. If we have a ZG resolution by projectives, so if I try to compute homology, this is also Z resolution, or maybe Z1 resolution. So the thing is that I may define a natural map from HIGA to H1 trivial group A just by forgetting the group structure. No, of course, this is trivial. This homology is trivial. And there is yet another map, natural one, back to GA. And this is like if you have a function. Well, if you have an element here, basically this is the thing that we looked at last time. We take the sum of its G shifts. The composition of those two maps is multiplication by n, because they have elements here. So if I started with something which was G invariant here, recall that when looking at this resolution, I'm taking the G invariance and computing the homology of this chain complex, I'm getting the group homology. So if I had started with something which was G invariant and follow these two lines, I'm just taking, here I'm doing nothing, and here I'm taking n times whatever I had before. So the composition here is just multiplication by n, but of course it's factored through this trivial thing. So this is the explanation. And in particular, if multiplication by n is an isomorphism of A, if A is divisible by n, if A is a vector space over characteristic prime to n, then multiplication by n should be the identity on cohomology. So then HIG is 0 to begins. So then so this is just a abelian cohomology, but now here's a nice conclusion. If U is a unipotent group, H1 prime. Then H1, now this does not make sense anymore for higher, again, for higher cohomology, again, can't see, and it is assumed to be 0. And this is strict. So this follows by
I'm sorry, but in the argument there, why did you use that I is vector?
what did I use this?
But if n is the characteristic, then multiplication with n is not an isomorphism.
Sorry?
If n is the characteristic, then multiplication with n is not an isomorphism.
No, but before this,
Before this?
here, in H0,
Before this you don't.
so
So that's the characteristic.
so you can, so here I need this actually I need a check. So you say that I need this here, but not here. Is the claim?
You need the lines.
This is something I can check.
No, the group cohomology of the trivial group is not trivial in zero
Okay.
degree.
Here is the answer. That's a good answer. Yeah.
Could you repeat it, please?
The trivial group has cohomology in degree 0. Well, depending on mathematics.
Thank you.
Okay, here. So the thing is that this I would do by so U, a unipotent group is always nilpotent, and well, the characteristic 0, I can always break it up into pieces. I can. There is a filtration of these, such that the sub-quotients are vector spaces, and hence the proof follows by induction, looking at induction on the length of U or the nilpotent degree of U, using the long exact sequence of mid-C. So I can write down the relevant piece, and let me read the G's here. By inductions, these two are zeros. So the kernel here is everything, and it must equal the image, everything must equal the image, which is 0 as well. So even though we're doing non-abelian cohomology, it is enough to
U1 is central in U?
Sorry?
U1 is central in U? In the-
Oh, well, first of all, I can assume so. But
the long exact
okay, yeah. So for this piece, I need take this and so this is take this to be the lowest thing in the central sequence. And the thing is, d mu1 in order to run such induction. Or actually, maybe. You can either take the induction on dimension or just on the again on the nilpotent degree of U, so I can take the full center, whatever. Take now example 2. Take A to be GLV. V is a vector space. A will be that algebraic group. And now take a look at H1 G8. Now this is an example of the other way around computation that I was talking about. Now I want to compute this one. I will actually use the fact that this is isomorphic in the descent. So A is the automorphism group of V as a vector space. So this is a descent as a vector space of EF of V. Now, we saw previously G action on V. Oh, sorry. U take U to be V or V and V. And now this studies G actions on such U's, and we've seen in the course of the proof, which I just erased, that U will be isomorphic to E in terms of F with the G invariance for whatever action of the Galois on this vector space G. And this means that the forms of U are always F vector spaces of the same dimension. By dimension, I mean, the E dimension of U is the same as the F dimension of UG. By dimension, I conclude that that UG is the same, is F isomorphic to the thing I started with. So I have only one form for vector spaces. This is the thing. This is the one. What I'm saying, this is very easy because dimension is the only parameter, and this is stable, and I deduce this is living again. So this is a non-trivial statement. I mean, we follow this is isomorphism is non-trivial. So it was very easy to compute that one, but it's not a priori clear how to prove this separately. Even in the case, so let me summarize it. We have this theorem, which sometimes is called Hilbert-Knight. So in the case of dimension 1, it was proven by Hilbert. This was probably the 90th theoretic proof that H1G GL or GLN is in the case of n equals 1, this is just E star 1. This is the usual form that Hilbert-Knight is stated. And of course, in that case, this is an abelian group, and this is a standard homology. Now, having GL, I can compute SL. Take is V for us the F vector space or the E vector space? can apply a long exact sequence to this one, and I'll get something about H1 of Sn. And, of course, it goes to H1 of GL, but this is trivial. So everything is in the kernel, and the kernel is the image. So everything is the image of what? Of E star G. E star G, what is E star G? It's F star. And so maybe I'll one more term. And what is and here I'll have GL and F, right? The claim is that this is on, right? Because I can just put 1, 1, 1, 1 and something here. The field element in the corner and the determinant field would be itself. So this is onto, and everything is in the kernel, and I can do that this is how am I going in time?
17 minutes.
Hmm?
17.
Oh, okay, good. So now, here's, well, it's not an explicit computation, but just to mention, if A, over here, is OQ, when Q is quadratic, the form on B, then I'm just writing the obvious, coming from the identification of H1 with a descent set. So this is just forms of Q. Quadratic of binding. This is just a statement. And now a specific case I will take, and take now H1 G and take the symplectic group SDNE. So take e to the 2n and put on it the natural, non-degenerate, antisymmetric form, and this is a standard theorem in linear algebra that I hope you know. I'm not sure what's the name of it, Sylvester or Whitley?
Inertia.
Sylvester theorem, right? Saying exactly this. All forms are the same. I will not prove it, but this is a standard exercise in linear algebra. But as you see, somehow, okay, this we know. Sometimes, if Q is a quadratic form or symmetric bilinear form, the question of how many, maybe this third example, if G is the derivative of C over R, more specific, H1 of G is two elements, and ON is a group of is a set of signatures. So a form of a non-generate symmetry unique form over C, unique by their form over C. The forms are classified by the signature, which could vary from 0n to n zeros. So knowing, this is just to show that, for example, understanding those things, those non-abelian cohomologies, gives us a machinery to classify forms of various fields. And this is a non-trivial and important thing in number theory. And later on today, we'll see, for example, how to apply it over finite fields by Laurent's theorem. Maybe that. Let G be a close. F close. That E is leading field. Of G. So this means G extended to E is isomorphic to E star some power. We can always find such a finite field extension that splits Y. And another one to say, so my claim is that H1 G is sorry. This claim is basically saying that H1 of a torus, if I'm willing to take G big enough, I'm willing to go high enough in my field extension, it is always finite. I guess take M to be the size of G, and let's consider T, which is multiplication by M, sorry, M power. If I use N, I mean M. I use it. This is the count. So S is finite. Right? After extending to E, on each component, if I'm taking the mth power in E star, then S will become the group of roots of unity of order n. So this is something finite. It will be the nth power of it after extending in E, and of course it will be some finite, some subgroup of that one if I'm looking only at the f powers. In any case, this is the finite group. And well, here in this box, going to homology to H1, this map becomes 0, right? Because I took the right power. This is why I bothered right now with that exercise. So H1 GT is actually in H1 just taking values in that S, hence 1. And now everything here is finite. This is less on Z1.
Do you mean less? No, less. You just have a subjective map from H1 to S.
I want to prove. Thanks. This means that in H1 this is subject. Thanks.
But I'm confused. So this is not in the argument we had before was in the Boolean convention.
No, but now everything is a billion. T is a billion. So now, indeed, I was looking at some abelian group. So I'm not doing this. Yeah.
I was just confused with
Yeah.
what's written by it.
I'm not doing this example just for fun. I will use it later on. Later on, I will prove some finiteness of cohomology for other groups. And the nice thing about it will be that well, I will be using heavily the structure theory of algebraic groups. And the fact that in a reductive group you have plenty of tori, etc. And eventually, so using structure theory, you reduce things to the abelian case, which you can solve by standard techniques. This is every step. Every step is kind of trivial, but altogether this is a not so easy thing to do. How am I in time? If I have a few minutes, now then I want to discuss, I don't want to start land theorem now, which is yet another issue. So let me discuss, up to now I was taking time and discuss the extension of this theory to non-finite extensions. So, so probably you do know that if I'm looking at the abstract Galois group of the field F, by definition, this is the Galois of F bar over F0. Let me think characteristic 0, so I have no probability issues. And this is the inverse limit of the Galois group, so of E over F, E finite Galois extension. And naturally I have the structure of profile group. Is there anyone who sees this for the first time? Mr. Mark? And when I'll do descent, I can ask about descent of FV without specifying E here, and then assuming always V splits into some finite expansion, then this is every friend of V, every descent friend of V, already can be seen as isomorphic to V at some finite field extension. And now, inside the limit, I know that there exists H1. It's just writing what we know. And this is the same. Now, if you want, this is the same by definition of that one. can view this as the definition of the right-hand side, if you want, but also it can make sense to define it separately. I mean, this is a group, and you have a natural Galois actions, and if you consider topology, continuous action is such that. Okay, maybe I can write down continuous here and erase these dots of definition, and this makes sense. I mean, you can define this yourself in a natural way and see that it's the same. So again, I will leave this as an exercise. Many times, I would be happy to understand things not without specifying the field of the expansion field E, just arbitrary descents. For example, if we go back to this example, name of term. Theodose. Then I claim H1 T. Now, if I'm not writing anything here, let's agree that this is with respect to the absolute level. I have no specific field extension, then this is fine. The proof is basically that example and the fact that there exists E finite over which this fits. And now you might want to consider the absolute Galois group. Take the Galois group of T. Here, H1 F T. Here I'm taking the relative Galois group. Gal E over F is isomorphic to gal F. Got it, right? I was applying to the relevant short exact sequences of groups. This thing, and this is exact. This is not the same exact sequence that I was using previously. I used the extension on the G level. And what do I know now? This is finite. This was the example computed before. And what can we say about this one? Actually more finite.
Just one.
It's just one. Why?
Because it's a torus.
And y is 1 for those. There is a name for this, which we mentioned. one-dimensional tones.
Don't we have to flip it? The restriction is from the bigger group to the smaller group.
My arrows are upside down. Yeah, yeah.
Value F is bigger
Yes,
than
yes,
our-
yes.
TE should also first you change the E's and the F.
No, it's TE. The group that I'm acting on is the same. Now, what can you say about this one?
Change bigger. T is just direct product of
So I want to write down T of 90.
T is just it's a direct product of
All over E, T is just direct product of E stars. And right? Maybe. Oh, I got confused. I need that is right. Okay, so this is exercise to solve over lunch. I want to conclude that this is finite. Put things together. I think I messed up with.
It should not be TE. The T is the algebraic closure. Because we want the action of the Galois group.
Yep.
And then just invert
Yeah. T of the general closure in all places. Okay. I think I'll leave it like that and maybe explain further after feeding myself. Is that a good time to stop?